All right, so without further ado, we're going to begin today's session. Before Akshay joins on, I'll do a quick introduction of Akshay and what he will be presenting today. So today's speaker is Akshay Ballal, who is the Chief Product Officer at Fabheads, and today he'll be talking about composite design for additive manufacturing. Many of you will be familiar with DfAM, and that's primarily what will be covered in today's session. So Fabheads specializes in composites part manufacturing sector, and they have gone on to become the first company in Asia with in-house developed fiber 3D printing capabilities. Through his experience, Akshay will be providing examples on how the choice of materials and processes affect the quality of the final product. Akshay will also be covering design philosophy for making strong, optimized, and easy to produce additive manufactured parts. So a bit about Akshay himself. He graduated with a BE in mechanical engineering from the Birla Institute of Technology, Mesra, in 2017. He currently works at Fabheads as the Chief Product Officer. And at Fabheads, Akshay has headed design and development of carbon fiber composite printing technologies and has also built several 3D printers leveraging the continuous fiber printing technology. So without further ado, please let me give a warm welcome to Akshay to join on board. Akshay, please go ahead.
Hi, good evening, everyone. Hope all of you are doing well. I think most of you are from college. You would be missing college right now since most of your colleges haven't started. But yeah, you're making the best use of your time over here. So today I'll just shed some light on how design for additive manufacturing works. Uh, so how we as designers should think for making a part which is going to be manufactured eventually with additive manufacturing. So as Kathy has given a quite a good introduction about me. So I'm a graduate from BIT Mesra. I graduated in mechanical in 2017. So I was a chassis and vehicle integration head in a team called Firewood Racing. So this was an off-road ATV vehicle, and we used to take our cars to an event called Baja. So it used to happen in Indore, Coimbatore. So I built 3 cars throughout my tenure at Firewood Racing. And currently, after my college, I joined Fabheads as a mechanical designer. So I've been making machines at Fabheads since 2017. So these are the some of the machines that are in our lineup, which are commercialized right now. We are providing services using these machines. So I'll just begin with a short, brief introduction about how additive manufacturing came about. We all might be thinking it's a very new technology, but if you see here, it all started out in 1981. So 1981 was a time when like CAD was just a beginning, and still they're making 3D stuff out of automation. So it started in Japan, where some scientists were experimenting with SLS technology. So it started out there. And in 1989, the most clutching moment in additive manufacturing is when Stratasys patented their fused deposition modeling technology, which is the most accessible technology right now, which you see in 3D printers. Then over the years, a lot of developments were made with different materials. So SLS was made for nylon and metal. Then in 2012, around in 2009, so every patent expires in 20 years. So the Stratasys patent expired in 20 years in around 2009, 2010, and there was a sudden boom of lot of companies who are in the 3D printing space. So around 2012, there were a lot of 3D printing. You might have heard of Prusa, MakerBot, desktop FDM, and they made it really accessible for colleges, students, and all to get their hands dirty with 3D printing. And if you see the present day, a lot of innovations are still done every day in additive manufacturing. So we at Fabheads are innovating a lot in composites additive manufacturing. There are other companies like US who are developing high-end versions of metal 3D printing, and there's a lot going on every day. So just a brief, this shows you where the additive manufacturing stands today and what are the different systems that are available. So some are not accessible in this, like only big industries have access, and some are very accessible even for student. So there is metal additive manufacturing, which has different forms. There is Samoset is epoxy additive manufacturing. Then there is a thermoplastic, which is the most used, which you see 3D printing. So that is the FDM process that's there. SLS is a very niche segment of the thermo where you use just mainly for nylon. And there's composite CM, which we are doing where continuous fiber print. And there are a lot more. These are the broad segments that I'm showing over here. So why does additive manufacturing even exist? So why is there all this hype about it? So one is it's really fast. It is a rapid prototyping process. Like so you can like without even making a tool for a part. Like if you want to make like a part initially in older days, either do a CNC machining of it, which requires you to take a big chunk of material and remove material out of it, or it would need you to make a tool and then cast into it, which so there's a tooling cost involved. And then so for initial prototyping that doesn't make much sense because you have to invest a lot of money. So that's where 3D printing and other additive manufacturing technologies come in. So it lets you quickly iterate your ideas with different materials and reach a design very quickly. And it also removes some of the constraints that are involved in other manufacturing processes like casting or CNC, and frees up your design thinking more, so you can test out even weirder, more crazier ideas. And it is economical for lower volumes because you don't have to make all that tooling, you don't have to buy a big chunk of material to cut out of. So those things are removed. You just need a printer. So it does depend on what kind of additive manufacture, but as a general rule of thumb, it is more economical for lower volumes. So when not to go for additive manufacturing, so you'll understand more about this as we look into how we design parts for additive manufacturing. But just as a general rule of thumb, simple parts which are readily available in the market off the shelf, and even if you're machining it, won't require much processing on it. Those things don't are not a really good candidate for additive manufacturing. And thin-walled parts, which are like less than 1 mm, very flimsy parts, those are also not that advisable to be made using additive manufacturing. And transparent parts, that is, or glass, as there are some companies who are working out with transparent parts, but still not mainstream yet. And it's not you can't 3D print. And most of the 3D printed parts which are transparent would be mostly translucent, and you can't print glass these days. So let's quickly begin with the topic of the day, that is design for additive manufacturing. So if you think about design for manufacturing, I'll show you where it stands as in a complete design process. So when you design a part as a designer, you have to basically think about three aspects broadly. So one is whether that particular part fulfills the physical requirement that it needs. So that would be whether it can take the strength or the loads acting on it, whether it can work in that operating temperature, whether the environmental conditions favor it, does it wear out, does it rust. Those are the conditions, so which can be validated using your FEA processes. Then we see whether it fulfills the functional requirement of the system, which can be out of a product specification sheet, whether it is actuating the mechanism at the right speed. Those are the functional requirements. And then you look at the manufacturing requirements. So whether it will be manufactured, how economical it will be to manufacture, how much research has to be done in just how to manufacturing that. You always try to reduce that. That should always go for the methods that are already available to you, and you don't have to reinvent the wheel every time. So for this particular session, we will look at a brake pedal. You all also, because you might have seen this everywhere, so it is an easy thing to go through. So brake pedal, if you guys don't know, it's a normal lever. So it has a pivot an action point which can either pull a brake line or push against a oil cylinder, and a trigger where your foot acts and your car brakes. So we'll go through the design of such a part and what decisions and steps you have to take on the way. Just to give a rough, like a very simple idea of what design for manufacturing is. So if you see a pocket over there, if it had sharp internal corners, you wouldn't be able to make it because the CNC tool just can't penetrate. It has a radius. So you always get a radius. So by designing itself, you give that corner. You won't have to. If you really need a sharp corner, you would have to do EDM or something like that. But if you can just give a radius over here, you wouldn't even have to think of EDM because you make the design such that it can take the more economical solution. So these are the main steps which you would take for designing a part for additive manufacturing. The first is the material selection. It plays a crucial role in for selecting what kind of process you will be going for eventually. So based on the material, you will be going for one of the processes. Then there is a topology optimization, which is mostly an advantage of having additive manufacturing at your disposal, and then specifying the manufacturing direction. So you'll understand what direction I'm talking about through the slides. Then reducing the amount of support materials and selecting the infill density. So with material selection based on what is the intended role of your part, you will be selecting materials. So if you're going for metals, so you would choose metals. If you need very high operating temperatures, you need higher wear and tear resistance. But this ends up being more expensive because the metal additive manufacturing techniques these days are not that accessible to everyday user. And but if your parts are like you need lighter parts which don't take that many loads, you can go for plastics, and plastic 3D printing is very common these days. And then there is a third type of material, that is composites, which we expertise in. So that is for very high strength light parts. So composites here I'm talking about is the fiber composites, like carbon fiber composites, which you might have heard of. So this also gets more expensive than the plastic 3D printing, and this is a technology that's coming up right now. So let's say we want to live on the edge, and we decide to make the brake pedal out of plastics. So, but in a general case, what you would do is brake pedals require more stress. You panic brake, and also those can be metal, but accelerator pedal or something can be made of plastic. But let's say we living on the edge, so you go for plastics. So topology of you might have seen pictures like this coming up a lot, where you see like this fancy, crazy parts with this kind of a lattice structure in between. So this is nothing but topology optimization. So what topology optimization does is it gives you the most lightest part that is possible with the given functional features, which will be of a certain safety factor based on your loads. So what I'm talking about is, so let's say I go through the process of what is topology optimization. So basically it gives you a very light part. So you first create a rough design of the part. So as shown in the middle, where no material is removed, it's just a general thing which you would think of. Then you fix certain features which you don't want to go away. So these are your hinging points, mounting points, and actuation points which you want to keep still in your design. Then you apply some boundary conditions, so where your load is going to act, which is a fixed geometry. So it does some calculations. It's like FEA basically, and gives you the most optimized part designs. So you should always take the designs that are thrown by the software at you with a grain of salt and do some analysis on those optimized designs yourselves. But it gives you a direction to think on. You can remove material over here. So you take the validated output design, that is, you do some validation on it, and then clean up the geometry, because it would give very random shapes which are not possible. So you clean up the geometry a little bit, and you can get the final part which is lighter than what you started with. So this actually is a very old technique, but it has come up a lot in additive manufacturing because of the more fancier shapes that can be fabricated. Like more, some of the shapes that topology optimization can give cannot be done using any traditional process, and it needs additive manufacturing. Something like what I showed you earlier. Like this isn't possible with your traditional processes. So next is print direction, which I talked about. So what is print direction is, so how additive manufacturing or 3D printing works is you start at, you print on a platform and you extrude over it. So layer by layer, you keep building the part. So you have a certain direction of printing. So in most of the processes that I showed you, like in that big chart, all of them act layer by layer, and it will be always weaker along that direction, along the print direction. So, because of this, you can see like parts usually fail along that direction if not designed properly. So, just a small quiz, you can think of that. So, which one of this do you think would be the most ideal way to print our good old brake pedal? So, the along the top is this lines which are shown are the print lines. So it's being built from the print platform. Yeah, I'll start with A. So what would I won't give the answer, but I'll tell you what would happen. So in A, when you apply load, so all the layers are built on one on top of the other. So the addition between them is not that good as the homogeneous part itself would be. So it is found that it is almost half or less than half the strength of the planar strength of the part. So this is called an out of plane strength, which is much less. So in A, what would happen is when you apply that load, you would have something like this, what you see, the bottom part, which is broken. So layers would just delaminate another from each other, and the part will break much easily given the load. Then in C, what would happen is if there is any deflection in the part, we know that the bottom, in a normal bending scenario, the bottom layers try to compress and the top layers would try to have tension. So this will have, you will have a difference in the strain in the part. So that will delaminate the layers again. So the best would be going for B, where all the load is acting in the plane, so that could give you the most out of the part. But you know that for this brake pedal that would work well, but there are some scenarios where load doesn't just act in one plane, and load can act in various planes. So there are measures for that too. So even what we do is we once the part is printed, we wrap it up with composite carbon fiber material, and that gives you that out of plane strength as well. So you can look up more on that. So that is overlapping of a 3D printed part. But yeah, so you need to take care of how the part is going to be printed, because that will decide things ahead of you in the pipeline. So you always have to keep that in mind. So next is support material. So let's say we have selected B for printing. Now let's go ahead. Now we see how the part is going to be printed, and how that again falls back on how we should design the part. So what are support materials? So support is, so since you're building layer by layer, and if the certain layer doesn't have anything to support it below it, so mostly the layers are supported from each other. So you can see over here the pillars that you see over there are the support. So they support the certain layer which don't have anything below them. So in our part, if you print it in how we told B would be, you will need supports where that lever part is. So the orange color things you see are the support materials. So support materials decrease the fabrication time, because your printer or the machine would always come there and print some support material which has to be removed anyway, and it would give a bad surface finish at that point, because you won't have a continuous layer to print on. So you need to reduce support material as much as possible as from the design point. and what kind of support is selected, and the density of support is mostly the machine's what do you say, capability. So that's more of a machine setting. But as a designer, you can always tweak your part to reduce the amount of support. So, general rule of thumb: any overhang that is less than 45-degree will need support. So this can vary from printer to printer or machine to machine. But yeah, so any overhang of less than 45 would so with the horizontal, if it is less than 45, you won't one second. Yeah, you can see that. Yeah. Yeah. So how will we change this design is, so you bring down the labor part. So this is if your functional requirements are satisfied. You always need to think about your functional requirements. So whether this will help you or not, you just have to go back again and see your functional requirements. But this will help you in manufacturing. You bring back the labor part down so that your support is gone and you are still able to make the complete part. So so what additive manufacture even allows you to do is reduce the number of parts that are in your system. So generally, if you're going for machining this part, because tooling would require a lot of money, you don't want to put money in tooling. Let's say the next best thing is machining it out of a big block. So in that case, what you would think is, because this lever is just a simple slab of material, you make that separately and just weld this other brake pad to it. So that would be an ideal thing to do if AM wasn't around. But with AM, you can do it in a single part. So, which is a much more robust way of doing it. Similar thing goes with many other things which have to be made in multiple parts, not just to save money, but the process just doesn't allow it. So in this case, you can see conformal cooling channels. So these are usually made in multiple parts where you make the channel in one part and you put the whole thing inside another jacket and then close the whole thing and put many seals in it. It just makes the process of making the thing more complex. So with additive manufacturing, you can just make this whole thing in one go with the channels already made inside it. So it has many. This thing is used in injection molding dies and all, where you need to do some rapid cooling in the die. So what I've shown here is a part of the die. So the top picture. Then is so what manufacturing allows you to do is it allows you to control the inside of the part. So if it's a thick part in a normal CNC or casting processor, it would remain solid from the inside, or you can give it some wall thickness. But introducing some kind of a middle ground is very difficult, where you have a bit hollow, a bit solid part inside. So that's what our lattice structures you can see in the image there. So what AM allows you to do is control that density that's inside the part. So the uh, the creation of this is automatically generated by the software which you use for additive manufacturing mostly, but you need to specify what is the percentage, and this is going to play a big role in what the strength and the weight of your part is going to be. The lower the density, the more hollow and more lighter your part will be, but less strength it will have. And more the infill, the heavier your part will be, the more strength it will have, more towards the solid block itself. So so this is the main thing you can control with them. So these are the things you have to consider when looking into additive manufacturing. So the first is your material selection. Then you can optimize your topology based on your design and the features that you have. Then you have you reduce the amount of support material there is. Then you can even reduce the number of parts that are in your system, and then you control the density of the whole part itself. So looking into what future beholds for EM is multi-axis 3D printing. So what multi-axis 3D printing allows a designer to do is he doesn't have to care about the print direction that much. So you can print not just from a platform, but can have another mold that is there and you print on top of it. So it gives you more freedom basically. And composites additive manufacturing is becoming mainstream. So you can make very high-end end use composite parts which can be used in very high strength applications. And more plastics eventually are becoming 3D printable. Like many new plastics are coming day by day, which makes 3D printing more accessible and more efficient. And there are many bigger machines that people are making to like print a whole boat, a whole wing structure in one go. So this is what the future of additive manufacturing will hold. So thank you guys. Thank you for sticking around. And yeah, if you have any questions, you can drop it in.
Thanks a lot, Akshay. So students, sorry, we have Akshay has finished his part of the presentation. If you have any questions or queries, please feel free to post it on the chat box so we can have them cleared. Akshay, we did have a question from Tirth Lodia. That was during the time when you were explaining from worst to best scenario.
I'll just go to the questions. Just a second.
His question was, what about parts handling pressure? I believe this was when you were still talking about A, but I've asked him to clarify via the web chat. Okay, yes, let me just, he's responded, just a second. Okay, there you go.
Yeah, so during pressure, so you have to see the like how the load is still acting. So you need to see what is the stress that is generated in the part. But as I said, it's not always a easy scenario. So with pressure, you will have hoop stress and they will have axial stress as well. In that case, you need to go for a overlapping or something. But in a much simpler scenario, what I showed, like mostly this works with brackets and all, where you have load in certain direction only. But yeah, with pressure, you might have multi-planar load, and you'll have to take further steps for that. But you can choose. So hoop stress is usually a lot more. So in that case, it's better. Let's say you are making a tube which is going to hold some pressure. It's along the axis of the tube. If you print, would be better.
Sorry, just 1 second. I'm just posting the next question. This question, Akshay, if you don't mind just reading out the question, because in the recording they won't be able to see the web chat.
Yeah. So Parth Dedia asks, which software do you suggest for designing and for structural analysis of metal 3D printing? Will SolidWorks and Ansys do the job for us? Yeah, absolutely. Do the job. So it's not much different from designing a normal part. You just need to take care of the out of plane strength, which you can always feed into any analysis software that's out there. You can make your own material sort of and give it strength which is low in in that printing direction, and you can analyze with that. But yeah, Ansys can do it. Yeah. Just saying. But yeah, so you can make a part which is not 3D printed, like you don't consider, and make that good first, and then you can bring in the 3D printing aspect of it. Yeah.
Okay. Akshay, before we take in the other questions that will come in, I wanted to probably, if you don't mind answering, you've been with Fabheads since pretty much like almost the very beginning, like before even the team had an office.
So I actually even interned before joining.
So right. So I wanted you to, if you could just say how was that experience? Like you took this jump on interning with a startup, and then now you are the chief product officer. So if you can like briefly summarize how this journey has been for you.
Yeah, it was a very tremendous, very big, good experience. So when I entered back in my fourth year, so it was just our CEO Dinesh who was with me. So I had a 2 month internship and got to learn a lot about machine design back in. And after college, I did get placed into some of the campus companies, but the job description didn't really strike me. So I joined this. I had got a PPO from Fabheads. Started out with as a mechanical design engineer. I built the first printer that we have, and you get to learn a lot staying at a startup basically, because you own the whole thing. You kind of run the whole process from the beginning and you see it off till the end. So you get to learn a lot more. So that, yeah, there is a lot of pressure, but it's worth that. So I got to learn a lot during this time. Yeah. And still learning actually. So it's never the end. It never stagnates basically.
Thank you for sharing that, Akshay.
Yeah.
Parth had another question for you, which is how should we account for shrinkage in metal 3D printing?
Yeah. So metal 3D printing. So there are a few ways. So you in your 3D printed part, so you always try to reduce the amount of corners that are there. So that is one point. So you have less sharp edges in your part, so that reduces a lot of. So basically, shrinkage, just the shrinkage itself can be accounted for. So when you give it off to a 3D printing guy, he will account for just the shrinkage, so he'll make the part a little bigger. But what shrinkage might cause is a warpage of the part, and in that case, having a more bigger surface area at the bottom of the part is a good thing, and that is something that the 3D printing guys take care of. They start with a slab on the bottom and they print on top of it. So it's not a big concern in metal 3D printing. So it will be taken care of by with the machine settings and the machine software. There are certain ways where you make the part in the anti-warp shape. So after it warps, you get to the correct shape. But those are more advanced softwares which are not really required for simpler parts. Yeah. Next question I'm seeing is I'm a beginner enrolled into mechanical very much in this part. What would you suggest for me to grow? So start. Yeah. So as an FSA student, so you can start if you want to grow in this particular field. If you're asking that, you start incorporating a few of your parts with and make them using additive manufacturing. It might fail initially, but that's the beauty of additive manufacturing. You can always keep iterating, but you can start swapping out your normally traditionally made parts and make them out of additive manufacturing. You can get a lot of experience with that and design better parts in the future. If, if I got the question right.
Akshay, I have a question for you.
Yeah,
Now, design for additive manufacturing has come very recently, you'd say in the last
yeah.
maybe I'd
It's a
say
new
5 to 10
process. So
years.
yeah, so
When that
yeah,
exactly. Yeah, so design for manufacturing was very, I mean, is still very prevalent. How, when
yeah,
you started in with Fabheads, uh, like, did you were these learnings there, or like, did you have to find many of these things by yourself? How did you go about this process, which is, for additive manufacturing? Because you built a printer
yeah.
as well. I'm sure it was
Yeah.
quite a bit. So,
So right. So there are a few things. So design for manufacturing is two steps, two things that it reduces. So it's there's always a dialogue between the manufacturer and the designer. So it's not just like you give away the part and they just blindly do that. So there's always a dialogue. So they will come up with some feedback, and you incorporate those feedback. It's never just one-way streak. But what design for manufacturing allows is you get so during my time there, yeah. So we had some Dinesh, that's our CEO, being from ISRO, we had some idea about my, but still, every new part has its own problems, and we did get that feedback. So there were many problems with how the parts, some parts had to be divided into more parts just to reduce. So all those are there. But what is thinking about it earlier, what it helps you to do is reduce that time, that dialogue between the manufacturer and the design. So you don't have to go back and forth, and you're at the right thing always. So yeah, during my time we did face some issues, but yeah. So if we had thought about it, incorporate more or DfAM, it always helps you. Yeah, I'll take questions for another couple of minutes. I think that should be fine, right? So another question: what are the advancements in material properties
Yes,
like
I'm
elastic?
actually not sure whether the internet connection is bad from my end, or I think it is bad from my end, which is why I'm having a
Yeah.
hard time hearing.
So
Please
is
go
it
ahead.
possible?
I have
Yeah, is it possible to 3D print a material having properties of mild steel or say titanium? So material itself, you might not get the same material. So 3D printing materials, like I said, you have some restrictions. You can't just take any material, even in the metals. If even if you have titanium, which you can, so a certain alloy or certain property of titanium can only be printed. So you always have to strike a balance. You might go for property matching, where you go for some other material that might have resemble the property, uh, but yeah. So on, like if you take for example steel, only the brittle types of steel which are can be printed. So usually the 3D printed metal parts are very quite brittle. You need to do some processing to make it less brittle, but they are never elastic. So that is still in development, but as it stands now, 3D printed metal parts are elastic. So, but thermal properties are quite good. Yeah. But yeah, not every part can be 3D printed. So next question: how effective is chrome plating on FDM when compared to metal 3D printing? I didn't get the question, sir. Yeah. Just chrome plating, if you're asking, wouldn't change the strength of the part. It might make it more wear resistant, but I'm not sure if we can do a chrome plating on a plastic printed part. And the last question I'll just take: how to decide how much fillet is required at internal edges 3D printing process. So this is something. So a 2 to 3 fillet would be good, because the smallest depends on the material. So the smallest drill bit, which end mill that they can use is around 3 mm. So you will end up with that fillet. So it's not like you design it, but you need to account for other things that might cause problems due to that fillet. So you put it in your design, and then you can check. So around 3 to 4 mm should be good. Yeah. So
Akshay, there was one question I believe you missed out, which was from Nisar Doshi, which is based on parts doubt about shrinkage. Any specific changes to be made in dimensions while part designing?
while designing, you can design the part. So it depends on how you are going to manufacture. Whether you are going to do it yourself, like you have a printer and you're doing it, or you're giving it out. So if you're for starts with the simple, if you're giving it out, you don't need to worry. You just specify the dimensions you want to end up with. Everything else is taken care. So because that is more of a manufacturing requirement. But if you are doing it yourself, just having it slightly, you try it out first. Like how much is the shrinkage? It's hard to, because it will shrink differently at every point in your uh, every point in your part based on how the thickness is varying, and also you try it out, predict, then you see where are the differences coming and what is the kind of tolerance that you're looking for in the part. Based on that, you can make the changes. But during design, so you can't really eyeball it. like it will shrink this much at this point, this much at this point. You can't tell that. There are some advanced softwares for that, but as a normal thing, I can start out with a non-shrink version. It doesn't really play that big a role initially, but if it is a really critical application, then you can make a sample, look at what are the deviations, and based on that, you can make changes in your part.
Akshay, final last question I put over there, and
Yeah.
we've closed Q&A.
That's the 10th one, right? How effective is it to use threaded inserts and critical parts in place to cut threads in metal 3D printing? So critical parts. So okay, so if we're talking about placing a thread, so it's always good to have a thread insert like a helicoil or something. It makes the threads more what do you say robust. So metal parts do not take the 3D printed parts. They are very brittle, as I said. So when you thread, the amount of load the thread, just the small threaded surface can bear might not be high. So with the threaded insert, you can increase the contact area, and also it's better to use threaded insert. But in most low load applications, I think just having the thread in the design, as if it's a good metal 3D printer, they can get the thread in the part itself. Or you can give a much a rougher thread that is a finer thread, and you re-tap it with a much deeper thread. So you give a initial thread which is not that deep, and you re-tap it with a deeper thread.
Great. Akshay, I think those are the end of the questions. We've got a few thank yous for you via the web chat. So on behalf of Formula Bharat and all the participants here, thank you so much for your time, for taking this evening to do the session. We really, really appreciate it. It's definitely a different insight from the past sessions that we've had. And yes, thank you. And to all the participants who've joined in, please don't hesitate or don't subscribe to the Formula Bharat channel for more content such as this. Akshay, thank you. Do you have anything parting notes for students as we end this session today?
No, yeah, that's it. So you can thank you for joining this session, and you can always get your hands dirty with additive. It's the most accessible thing you can. If your colleges have 3D printers, so I think you can always take some parts and start manufacturing, which was not possible earlier. So, but now it's possible. So yeah.
Yes, the great thing about advancements in technology and about access in colleges as well.
Correct. Yeah.
Thank you, Akshay. You have a very good evening, and to rest of